Okay, so let me just begin by the two religions in machine learning. The first are frequentists, who love repeating experiments and who only believe in outcomes that they always see. The next ones are the Bayesians, who love to observe, guess, and experiment. And they will also believe in outcomes they've never seen before, and they love modeling uncertainty. I'm a Bayesian myself. There's another religion which I would rather call a revolution, and that's called deep learning, but I won't go into that now. So for an example, let's have a coin toss, and we've tossed it 10 times, and we only saw 10 heads. So if to a frequentist you ask, what's the relative frequency of tails, you'll probably not get an answer, because for them, a probability is a point estimate. Whereas for a Bayesian, probability is a distribution. So how a Bayesian thinks is that if all I know are that there are two outcomes, the heads and the tails, and there's no preference of one particular outcome, we would just assign equal probability to both. So you have a relative frequency of tails, which is then 0.5. This is something I found online, which says that a Bayesian is someone who vaguely expects a horse, somehow catches a glimpse of a donkey, and then strongly believes he's seen a mule. So what this says is Bayesians are very flexible, and the models that you develop would help you infer, think, and do a lot of strong downstream processing. And from many of the machine learning and deep learning conferences, I do see that there is an interplay between Bayesian approaches into deep learning, and I think this is something that we all should be really looking forward to. So, okay, one of the most important and common machine learning tasks when you're given a data set is that of clustering. What is clustering? It is to identify a group of objects where objects in a particular group share some similarities, and they're way more similar than objects in another group. So you could use non-Bayesian methods like hierarchical clustering or k-means, or Bayesian methods like Bayesian hierarchical clustering or mixture models. And the main assumption here is that one object can only belong to one cluster. So let's say you've applied some clustering of choice, and you get these different colors. Every color is a cluster. So in general, the kind of objects we work with are vectorial objects. By vectors, what I mean is you have n observations, and each observation is a d-dimensional vector. You can stack all these vectors and you get a matrix. Let's call it x n times d for n objects and d features. Now, this is actually just a subset of the data types that you can get from the entire universe of entire universe of data types, and this is what I show by the blue circle. So you can apply your favorite clustering algorithm and you get your clusters. Again, remember, your assumption is that one object only belongs to one cluster. So what if you're given objects that don't have a vectorial representation? For example, they could be protein shapes, which are 3D. Then you have chemical compounds, you have probability distributions, you have graphical networks. You also have lines of strings, for example, code. What if you want to cluster these kinds of objects? What would you do? So this brings us to identifying what's the way you can represent these kinds of objects that are not vectorial. And they're mostly available as pairwise distance data. This is one property that they have. By pairwise distance data, what I mean is you have a matrix which is n times n, where n are your objects, and they are now having pairwise distances between each other. And this brings us to the work that I've worked with Julia, which is called the probabilistic model for overlapping clusters of distance data. Meaning now you want to come out of this assumption of having just to assign one object to one cluster, but you want to assign it to multiple clusters at the same time. Okay, so now let's take a step back and see what's the big deal with distances. What I've shown here is a cartoon, but it will definitely drive home the message. Let's say we have two vectors, x1 and x2, that are centered at 0. And this can also be considered as two random draws from a Gaussian, which is centered at mean 0. And if you construct the similarity matrix, which is shown to the right, that is x transpose, you get the matrix shown there. We can assume this to come from what is known as a central Wishart distribution. A Wishart distribution is one that allows you to randomly sample matrices instead of just vectors. Let's say we rotate x1, x2, and you again compute the similarity matrix, x rotate transpose, which is again now coming from a central Wishart distribution. But you can see here that these two similarity matrices are the same. So when you move from X to S, you've actually lost rotation information, but you do capture the similarities. Now let's say we translate, so that is you shift the mean from 0, 0 to 3, 0, and then you compute the similarity matrix, you get a different similarity, and this is now considered to be from a non-central wishard. But the interesting thing is, if you compute the distances from any of these three similarity matrices, you're going to get the same distance. So now the interesting part is when you move from the similarities to distances, you've also lost information of the translations. So if you're only given a pairwise distance data, you have no idea what the series of rotations and translations were that were applied to your original data that brought you there. So for a more mathematical setting, these are just the matrices we saw now. X is the count matrix with n observations and d features. And if you convert it to the similarity matrix XX transpose, you've lost the rotation. And similarly, when you move from S to D, and this is the equation that I show there, you've also lost information of the translation. So this is a unique mapping. It's fine because you know you have the X matrix you started with. But if you're only given the distances, you want to plot it back because there are no methods that will allow you to work only in the distance space. You would end up getting different S's and different X's because you have no idea what the real X matrix was. So what we're trying to push forward is whenever we have non-vectorial data, it's better to work in that regime as opposed to embedding it into S and then D because these are non-unique mappings. So as I said, this is a Bayesian clustering model. What we have is our observation, that is the D matrix, and our interest is in observing Z, which is the cluster assignment matrix. And what does this look like? This is a binary matrix where every row is an observation and every column is a cluster. This has an analogy to the Indian buffet process, but I'll come to that in a few slides later. And this is the cluster assignment matrix. So every yellow square you see here is telling which customer belongs to which cluster. So in a traditional setting, you just have found one yellow square per customer, but here we're going to have multiple yellow squares or yellow squares per customer. So this is the aim. This is what you want to infer in this Bayesian method. And then because you're Bayesian, you have now the prior over Z. You have the likelihood that tells you how likely was the distance matrix to come from that Z. And then you have the posterior that tells you how much of certainty you have for having seen that Z coming from that D. So now let's look at each of these elements. The prior over Z is what is known as the Indian buffet process. The setting is like this. You have an Indian buffet happening. There are infinite number of dishes, and there's n people in the line. The first person comes in, samples a few dishes, gets seated. The next person comes in, samples probably the same dishes or some other set of dishes and sits in. At the end of this process, if you take a look at what dishes have been sampled and have been used, you can see that multiple customers would have taken a same set or different sets of dishes, and this is how the clustering process happens. So this technically is known as, works with the beta binomial prior. I wouldn't go into the details of how this is, but we have a small write-up that I have the link later on in the slides, and more than happy to talk to me after the talk. And because this is a Bayesian method, you also don't need to fix the number of clusters. It infers the number of clusters on its own. Next is the likelihood. As I said before, wishard is a distribution from which you can sample matrices. We definitely had to augment the wishard so it could now take in distance matrices. And so this is the entire setup of how it looks like. Definitely there's a proof and a theorem behind this. And the message is this distance that we now have, this likelihood, is both translation and rotation invariant. So you do not have to go back to find out what the X is. And then finally, the posterior that every Bayesian loves is to start having either a Markov, an MCMC algorithm, a Markov chain Monte Carlo. Here what we have is a Metropolis Hastings with Gibbs iterations. Basically, once you have conditional distributions of your variables of interest, you keep iterating until you find out what your exact distribution would be. So it basically asymptotes to your approximate posterior. And you do this for Z, and this is definitely a model of choice for many of these Bayesian methods. For anyone who's interested, this is a generative model. I do not have a pointer, but... Okay, so do I just do like... Okay, where do I point now? Okay. So this part here is the prior. So the Indian buffet process is this part, and this one is the likelihood. So if I invert this generative model on its head, so basically D goes up, then what I'm doing is I'm going to run my sampler and then start inferring Z. So this is what Bayesians love to do. They make the generative model, flip it on its head, and then run MCMC to get the variables at the bottom of the tree. Okay, so now we've run this model on 3 different data sets. I'll only show one here. The other 2 are unpublished data, so I can't really show it here. But so this experiment is done on HIV protease inhibitors. This data is publicly available. We have 26 approved anti-HIV drugs, 10 of which are protease inhibitors. So if you see it, oh. All right. So here, this is the cell, and these things that you see here are the HIV. And the rectangles actually show the 5 different types of anti-HIV drug categories that are present. Protease inhibitors are these 10 here. So we took that because they exhibit similar behavior, and they also have similar chemical structure. The problem is that they're not readily available. So it's definitely necessary to identify alternative protease inhibitors for therapy. And what we thought was, let's look at the chemical structure and find out how dissimilar they are amongst each other. So we compare it to what is known as the protein contact maps. Protease inhibitors are proteins, and as we know, proteins also have amino acids. So we take a particular protein, compute the pairwise distances between the amino acids, and then you have a distance matrix. And this is done using what is known as a contact map. And we compute the distances. We row vectorize it, so now you have strings of vectors. And because we have to normalize it, we use what is known as a normalized information distance. So we have the same thing that is applied to all the different protease inhibitors. So it's a variant of the normalized compression distance that uses Kolmogorov complexity. Again, this is there in the paper that I said we'll see later. The figure here shows you the contact map for the HIV-1 reference genome. And these are the contact maps for the 10 protease inhibitors. Once we ran POCD on this, we get 3 different blocks. The first block shows these 2 together. So this is atazanavir and ritonavir. They definitely go hand in hand, and they are always used together, and they're shown to be highly efficient. The next block had the last 5 here and these 3 together, and these are ones that can be used independently as well. The other block had just atazanavir here, the one in green. And this stood out pretty much because it has very low cross resistance and is known to not work on its own if administered. So this is definitely a protease inhibitor that we can identify that is different from the rest, even though they're known to look the same. And because of its functional properties, you can actually attack this drug and see if there's another that can be as an alternative for this. Okay, so with that, I want to conclude, although this is work in progress, so there's no conclusion slide. I just wanted to say that if you haven't understood anything I said, all you need to take home is that this is a method that is a Bayesian model that allows you to cluster an object into multiple clusters, and these objects are present as pairwise distances. And then this is some reading material I thought I should share. The first one is a very good exposition about anything and everything Bayesian. The second one tells you about the war between frequentists and Bayesians. And the third one is the abstract that we presented the same work at for the Bayesian non-parametrics workshop at NeurIPS last year. It was a spotlight. And the last one is a place where you can go and check out the latest and hottest deep learning papers, and everything that is mathy about it is there. Yes, so that's it. Oh, I'm sorry for the slide. Yeah, but okay, that's it. Thank you very much.
So can you just give an idea of how big D was in this case, and also what problems did you have during convergence? Did you have to tweak the data or anything?
That's a very good question, always a question Bayesians fear answering. So For the HIV data set, we had 10 protease inhibitors, but as I said, we had to make them string-wise. So this was 20,000 strings versus 20,000 strings, so that's how big D was. We had another experiment with single cell data, and this was again 25,000 cells versus 10,000 genes. And another data that we've tried this on is with young kids who have jaundice and who have been given phototherapy treatment. So that's but a small data set of 140, but they also have, can't remember, I think 30 features. So we have a span of data sizes that we've tried this on. The runtime complexity of the model is O n raised to 3, so it's n cubed. So this definitely gives us issues. So the code is now parallelized, so we can run it, but we have some ideas of trying to run embarrassingly parallel MCMC and as well as amortized inference, just to make the sampler go a bit faster.